Now the tutorial we will look at today is an introduction to the tidyverse in R. It is already uploaded here, so you can follow along if you would like to. You can also just watch, whatever you prefer. And you can also download the PDF document, or you can download the R Markdown file. Now, I assume that quite a few people who attend this course will not have much previous programming experience. Maybe for some of you, it is the first time you encounter not only R, but any other programming language, so you may not be familiar with it. R Markdown is a format which mixes text and programming code, so you get very small pieces of programming code and an explanation what this code does besides it. You can open the R Markdown code by clicking on this link, and then you open this. Unfortunately, to download it, you need to click on Save Page Under, and then you need to look at the correct folder where you want to save it. For example, this one. Of course, I already have the R Markdown file, so I'm not going to save it right now, but that's how you download the R Markdown file. Now, if you want to run the code, you either need to have R and RStudio installed locally. This is mentioned here as prerequisite. We also have links if you want to download it locally on your own computer. Alternatively, you can use the university's computer. They have this Connect website through which you can log in using your HRZ username and password. And they have R and RStudio pre-installed. So these are your two options to run the code yourself. So if you open R and RStudio, let me show you. This is what it looks like. This is what an R Markdown file looks like. You have code in these gray areas. You can run them with a click on this button, and you have explanatory text in the white areas. Now, for some of you, working with programming code may be new, as I mentioned. This tutorial is designed in a way that is also suitable for complete beginners. For complete beginners, I also have a few remarks on what happens when you write code. First, this change sometimes can be something that some people feel a bit uneasy with at first. But R has a very helpful and supportive community, so if you don't understand something, there are many internet resources, many forums, many people who can help you. That's the first part I'd like to address. The second part is that when you try to program, you are going to have errors. And if you have these types of errors, you might need a bit of time to find out what causes the error and how you can correct it. That's completely fine. It's also completely fine to take a second, but it doesn't mean that you are bad at programming or anything like that. These errors happen to anyone. From my experience, the most common cause of errors are typing mistakes. For example, people might try to access a file and have written the name of the file wrong, and so the computer gives a file not found error, which may be confusing at first because the file is there. But if the name has been typed wrong, then the computer cannot properly find it. So far for the theory of programming, and if there are no questions about that part, I think we should start with the R Markdown file. Now I'm going to run the code as I go along here, and the first piece of code I always like to run just to make sure that everybody understands how the whole system looks is 1 plus 1. The result of this code is probably not going to surprise you. I can run it with a click on the screen button, and of course the result is 2. Now, a programming language like R, of course, can do much more than a simple calculator. And R is also used in a large number of disciplines. But there are a few packages, a few R extensions, you could also call them, which are useful for nearly every scientific field. And one of these particularly large extensions, very widely used by researchers, is the tidyverse. You use it to work with data, with tables. I assume you all have seen tables. And of course, quantitative research exists in many different areas. Now, as I mentioned, the tidyverse is an extension, so it is not automatically downloaded with R. And you can install it using programming code that would be installed packages and then name the package that you want to install, in this case, the tidyverse. Now I put a hashtag in front of code if I don't want to run it, because I have already installed the tidyverse and I don't have to install it twice. But if you want to replicate the tutorial, you can install the tidyverse with this piece of code. And after you have installed it, you can activate it using the library command. You will have to activate it each time you start a new R session, each time you open R for the next time. So this part of the code will not get a hashtag because I have to run it every time. And you can see we already get a quite extensive reply from the programming language. Unfortunately, it's called warning, but this is nothing to be concerned about. The system did exactly what it's supposed to do. It installed the tidyverse. Some functions of the tidyverse have the same names as some other functions in R. So there can be some confusion about that. This is called conflict, what this part of the warning is about. But we will not encounter this problem in this tutorial because we only focus on the tidyverse. To install a package in R, you could also go to this package field here and click on install. So that's the clicking variant instead of the code. You will still have to pick the name of the package, and as you can see, R really has a large number of extensions, and there are also a large number of extensions working with this whole tidy concept. Tidy census, tidy CPP, and so on. We would install the tidyverse, but as I mentioned, I'm not going to do that because I have it already installed. All right. Now, the tidyverse is great. It offers many functions, but we will be working with an EXO file in this tutorial. So there's a second function we will need to download, and this is the readxl library. Again, I simply click on the button. Now, once we have everything set up, it's time to take a first look at the data. We first need to import the data in R. Any imported data set will become visible here. You could also import it with a click on this button, but again, we will use programming code. I have an Excel file already in my directory. It's called Statistical Review of World Energy Data. And if I click on it, I can either view the data set or import it. But we will see that if I click on the button, what it does is running a piece of code. And I even have the code shown here. This is very convenient because if I copy the code into the R Markdown document, anyone can simply run the code and arrive at the same result where I was. It would be much more complicated if I had to tell other people, click on that button, then do that and that. So instead, I simply have the code here. Now, the result, the preview that I get shown here is not looking too great. First, Excel can become fairly complex. Any Excel file can consist of multiple sheets. And R has a default sheet, but it also shows here all other sheets that this Excel file has. There are quite a lot of them. In this tutorial, we will look at oil proved reserves history. Now, this is looking more like the data sets many of you will probably be familiar with. We get informed what the data set shows. There are oil proved reserves in 1,000 million barrels. We have the year here, and we have the reserves by country listed here. We will want to skip the first two lines because they don't really add any information. This line is just empty like several other lines. And this line here just has the columns labeled. So instead we'll click on skip 2 and you'll see that two things happen. First, the preview changes. Now we have the columns named after the year. And second, this code changes. We now have the sheet named in the code and we have the information that we want to skip the first two rows also in the code. Now, going back to the R Markdown file, this is what the code looks like now. And this way I can open the data in R. The data also gets opened right away with the view command, so you can see it is looking the same as it did in the preview. Now, R allows you to work with quite a lot of different data types. I chose Excel for this tutorial because I think it's very widely used, but depending on what background you have, depending on what data is common there, there are many, many others. And there's an R package for almost every data format around. For data from SPSS, from Stata, from, I don't know, whatever you may think of. One very widely used format is the CSV, so I would like to show you how to work with that as well. With the tidyverse, there is the write CSV function, which allows to export our data as CSV. Normally you do it after you modified the data, but I just want to demonstrate it here at the beginning. And if I run this code, you will see that there is World Energy CSV now in the files. We can import this right back into R with the read CSV command. We can also use the import dataset functionality again, but I'm just going to run the code that I have written here. Now you will see that the new object has a different name, even though they are exactly the same data sets. This is because I assigned it to the name oil reserves here. So when you write a data set, R needs two informations: which data set you want to write. This is an object from this environment area, in our case, statistical review of world energy data, and how the object is supposed to be called in the directory. So in our case, that's world energy CSV. And it needs to have the correct file ending. So for write CSV, it needs to be CSV. If you read a file into R, you need some different information. You need the name that is supposed to appear in the environment pane, and you need the file name from which you import. I will go on and start with the data cleaning, because what we have now is 2 times the same table in the environment area, and that's not making a lot of sense. We can confirm that they are truly the same. We can simply click on it, and you can see they look exactly the same. So one is a copy of the other, and we can delete one of them. We can do this with the remove command and name which table we want to delete in the environment pane. Again, be careful about typing mistakes. In these kinds of comments, the system will not find the dataset you are referring to if you have written the name of the dataset wrong. And of course, you will want to be careful not to delete data you still need. This is probably self-explanatory. Now, next, we will try to clean up this oil reserves data. You probably already noticed that it's looking a bit weird with these types of grayed outlines. We can also see if we move to the ending of the data set, it has data until 2020. And the other lines all have years. The other columns, I mean, all have years as headers. But these ones have 3 dots and then something behind the years. And we will remove them because we are not interested in them right now. We will only want to know for a specific year what were the oil reserves in these years. If we want to remove a column, we can use the select command for this. Select is one of the typical and very widely used tidyverse commands, and you use it as the name suggests to select. You select columns. You could select the columns by name. You could select the columns by position. So this would be the first column, second column, third column, and so on. What I will do here is using a negative selection. So what this command says is select all columns except the ones at position 43, 44, and 45. I could assign this to a new variable, oil reserve selected, or however I'd like to name it. On the left side of such a comment, you can write anything you want. But I am going to do what is called an in-place modification. I will just remove the columns from the oil reserves table, and the new table will replace the old one. As you can see here, the number of variables changed here. It changed because variables in R are interpreted to be columns. So when the system says 42 variables, what it means is that dataset has 42 columns. And this is the case because of the tidy data principle. As the name suggests, the tidyverse is based on the tidy data principle. So I think it's worth taking a second to explain what this principle is about. The tidyverse data principle says that all columns are variables and all rows are observations. In that sense, every tidy data set is comparable. And this is important when you work with data because it is much more complicated to work with data where every data set has its variables organized in a different way. And you can see there are quite a lot of ways in which data sets can be non-tidy, or how Hadley Wickham called it here, messy. For example, it could be switched. The rows could be variables. You could have variables in both columns and rows. You could have multiple variables in a single column. And it means that when you run the same comment on different data sets, in some of the cases it may not work. In some of the cases it may do something completely different from what you intended. You need to know where the variables are in the data so you can work well with the data. That may sound obvious, but it is not necessarily extremely easy to answer. Let's get back to the oil reserves data. What are the variables in this oil reserves table? How many of them do we really have and where are they? Can someone tell me that? If you think about how many variables a data set has, it can be helpful to name them. And if you name them, you will see that this data set only has 3 variables. The variables are the country name, that is in this column, the year, this is in the header, and the oil reserves in 1,000 million barrels. They are in all these 41 columns. So we have a data set that is very spread out. We still have this weirdly named column 42. It contains data from 2020, but the name was not unique in the data set, so R added these 3 dots and 42. We will now rename it to simply 2020, so the data set is more unified. We will rename the 1,000 million barrels variable to country, because this is what it is. This column contains a variable, but it are not the oil reserves, it are the countries that have these oil reserves. So the title of the column is wrong. And if you look at the data directly, this is probably very intuitive that Canada, Mexico, and so on are not how large the oil reserves of some countries are. But if you try to process data sets automatically, if you don't look at the data sets, you might make mistakes if the data is not labeled correctly. So you should always have the data labeled correctly. And this is why the rename statement is very useful. If you give a column a new name, there are also some rules to consider. In theory, you can choose any name you want on the left side of the equation sign, but it should not start with a number. What we have here is very unfortunate. Ideally, it should not be a number. It also shouldn't contain empty spaces. Because if you have these, you always need to put these quotation signs in there, and it's not normally necessary if you use variable names that don't contain empty spaces and don't contain numbers. Now, to explain this code in more detail, you need to distinguish between comments that tell the computer what to do and objects. This is about what objects the computer is modifying with the comments. As we have all seen before, oil reserves is a table, so oil reserves is an object that we modify with the code. This object can contain several smaller objects. In our case, these are the columns. And I modify one of these columns with the rename statement. This sign here is called a pipe sign. It tells which data set to refer to. The tidyverse always works with data tables. They are called data frames in R. So you typically start tidyverse comments with the structure. You pick the data set you want to modify, and you put the so-called pipe operator here. Then you choose the tidyverse command, and as you might remember from above, this part of the code looks exactly the same for both pieces of code, but the tidyverse command is different. Here it is a select command, here it is a rename command. Depending on what command you use, you might have to give additional information into the brackets. In this case, because you want to rename a variable, you put on the right side what is the current name of the column, and on the left side, the name you want to give to the column. In the select statement, you do not have an equation sign like that within the brackets. Instead, you only list the columns you want to keep, or here, because I use the minus sign, the column you want to remove. Now, it is worth noting that in theory, in a file like this, you can rerun the code as often as you want. But in this case, it will give you an error. This is because this piece of code does several things. First, it tries to pick a column named 1,000 million barrels. And in the second step, it tries to assign a new name to that column. But I already renamed the column. It is called country now. The oil reserves table does not have a column named 1,000 million barrels anymore, so R cannot pick it. So I get the error, can't rename columns that don't exist. It used to exist, and this is why the code ran without problems for the first time, but it does not exist anymore. We already renamed it. And so when I try to rerun this, I get an error. If I want to replicate everything up to this point, I instead have to click here. This says run all chunks above, so it runs all code I ran so far. And now we have again the oil reserves table with the 1,000 million barrels column. So I can again rename it. And if I look at it now, I will see the column is again called country. This is something to keep in mind. I think it's a fairly frequent cause of errors as well. Now, the second point I will address in this first data modification is that the dataset contains many gray NA values. You probably already noticed them. Here's an entire row of them. Here's the next row. From the point of view of R, there is missing data in these cells. NA means not available. But depending on where the data comes from and how it is constructed, NA values can have different meanings. In our case, they are simply a result that somebody thought the table would be easier to read if they left a few rows empty. So there is nothing missing here. These are just empty rows. And that means we can delete them with no problem. And here we have an example of a tidyverse comment that does not require any further input. Again, we modify the table without changing its name. So we have this oil reserves code again. Then here we have the tidyverse comment, but this time we don't need to give any column as input. We want the NAs to be deleted in all columns. You could only delete them in some of the columns. In that case, you would give the column names as input here. But we don't want that. We want all NA values to be deleted. So we simply run this command. Note that even though this function does not require any input within the brackets, it still requires the brackets. Because these brackets are how R knows it's supposed to really apply this function to the data set. But what you can see is the difference if you run it like this. So what R does here is giving me the function definition. It's very technical, it's not going to tell you much, but if you ever get an output like that, it means you forgot the brackets. So always run a function with brackets, even if it doesn't require any input. Now, the other point that you may have noticed if you have been watching the environment pane again is that our table is smaller now than it used to be. It used to contain 99 observations. Now it are only 72 because almost 20 of them got deleted because they were empty. R always removes entire rows if you want to remove, for example, NA values. This is because what we are having here is a data frame. It always needs to be rectangular. You cannot have a data frame where you have in row 1 5 columns and in row 2 only 4 columns or something like that. You always need to have the same number of columns for every row and the same number of rows for every column. So you either have these NA values or you remove entire rows. Next, we will look at pivot longer and mutate. They are both more complex commands, and especially mutate is also very versatile. You can do a lot with it. I already mentioned that this dataset only contains 3 variables: the country name, the year, and the oil reserves in this year. So for the dataset to become tidy, we need to turn it into a format in which it only has 3 columns. Each of the columns will correspond to a single variable. To do that, we will use the pivot longer function. And this is what it looks like. It's called pivot longer because these are different formats but of the same data. So we keep the number of data points, and since we reduce the number of columns, this will mean that every column will become longer than it is currently. And this is why the comment has this name, pivot longer. Now, the beginning structure of the comment is, as you know it from the tidyverse, we address the table oil reserves, we use the pipe operator, we give the name of the function we want to call. But pivot longer is a function whose inputs may take a moment to be understood. What you do is that you say which columns you want to be summarized into typically 2 columns. Because what we will do here is that we make one column that will contain the header, it will contain the year, and another column which will contain the oil reserves values. And the header is addressed with names too. The new variable will be called year. The oil reserves in 1,000 million barrels are in the rows of the data set, so they are called values here, and these values will all be gathered in the column I named 1,000 million barrels. It are oil reserves in 1,000 million barrels. Now, I also need to define which part of the data set I will take the names and values from. Because there is a single column that we will not include in the comment, it is the country column. So here I define that this operation should be conducted on all columns except the one named country. The exclamation mark in this context means exclude this column, use all other columns. If you take a look at this above, you're going to see how the format changes once I run the code. We now have nearly 3,000 observations and only 3 variables. And as I mentioned, the 3 variables are country, year, and oil reserves in 1,000 million barrels. Now, if we look at the way this data set is structured now, we can see why it has become much longer. We still have the values for Canada, for example, from the years 1980 to 2020. But instead of having the values listed here, 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 and here, we now have them here, 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 and here. And this is why the data set became so much longer. The 41 first observations are the data for Canada, then we follow with Mexico, and so on. Now there's also the possibility to conduct this operation in reverse. Doing it in reverse removes this tidy data aspect, but a wider format may still be something you want for some reason, because it can be easier to get an overview over the data that way. I think that would be the most common reason. So we are going to take a look at what it looks in comparison. And now we will assign this to a new name. We will create a new object in environment because we don't want to overwrite the oil reserves. We still want to work with them later. Now, pivot wider also takes some arguments. It will spread out 2 columns across several columns. One of these columns will give the header. This will be the year. And the other column will give the values. This will be the 1,000 million barrels oil reserves column. And if we run this code and open the table it created, we will see that the resulting data set looks very familiar. The year is back in the header, and the oil reserves values are back distributed across the columns. Because working with the longer format is standard in R, is standard with the tidyverse principles, we will continue with the longer format, but I want to demonstrate that this can be converted in both directions and there is no information lost on the way. In theory, you can switch back and forth as often as you want, even though obviously people don't normally do that. They just switch to the format they need and work from there with that. Now, as you have seen, the missing data here is denoted as NA, not available as well. Unfortunately, there's no standard convention for data that gets released, how to denote that data points are missing. R has this NA in capital letters. Here it's in small letters and with a slash in between. So R cannot realize quite away that this is missing data. As we can see here, R treats these columns as characters. They are oil reserves. They are in principle numbers that we could do calculations with. We could compare, for example, how did Canada's oil reserves develop from 1980 to 2020. But we cannot do such calculations yet because R cannot recognize that these are numbers yet, because R will treat these missing data points as text, and therefore it will treat the entire column as text. A column can only have one type of data, and this column currently has the character type, which means text. So we need to make sure that this missing data is processed correctly. And for this, we will use one function within another. So what we have here is mutate as the outer function and NAIF as the inner function. NAIF checks if there is a certain value, and if it finds such a value, it turns it into the NA value that R uses. If we use it inside the mutate comment. We now see one of the advantages of the long format, because if we were still in the wide format, I would have to check for NAs in every of these columns separately. But now in the long format, all of our numeric values are in the 1,000 million barrels column. So I simply check within this single 1,000 million barrels column, is this value present there? If yes, turn it into NA. Again, we have to give the name twice of the column we are addressing, because I will simply modify the 1,000 million barrels column. If instead I wanted a copy, I would simply give some name for the copy here. 1,000 million barrels 2 or something like that. But I don't want a copy. I'm fine with the new column replacing the old one, so I will run this code. And now we will see, if we look at the Soviet Union, instead of the black printed letters, we now have the gray NA letters here. So R now recognizes this correctly as not available data. This column still has the character type, but we can change this now. To change this, we also use the mutate command. And within it, the command to change the type of a column is simply as numeric if we want to change the type from character to number. There's also the reverse command as character. There are many, many other data types, for example, as date, if you try to work with dates and years specifically. But I would say that as numeric is the one I use most frequently, because it happens really often that you load an Excel file or CSV file or so, and R does not recognize quite directly that one of these columns contains numeric data, because there is some NA definition, some type of entry that gets recognized as a character. And now, if we open the table again, we can see that these are now numbers. And for numbers, R can also give us directly in which range the oil reserves are. So there were some countries which in some years had oil reserves of 0. Other countries had up to 1,800,000 million barrels. So we are talking about very, very large oil reserves. Some other variable type that I think is more particular to R is the variable type factor. In principle, factors are text data. For example, you can turn the country column into a factor. You could not turn it into a numeric column because it does not contain numbers, it contains text, but you can turn it into a factor. What differs factor from the character type for a column is that if a column has the character type, values within this column may be nearly anything. With factors, on the other hand, you can define certain categories. You can say, for example, values in this column are allowed to take on the value low or the value high. What I will do here is I will define this country variable to be a factor, again with the mutate function. And then, at first glance, not much has changed, but you will see that this is a factor now. And factor variables can be summarized with this fact count. So now I have a table which shows me what values are in this column. In our case, these are the country names. and how often do they occur in the column. And we can see that we have a balanced panel. Every country is exactly 41 times in the column because the dataset contains 41 years. Now this fact count is a bit different from the other comments we have seen so far. First, we don't use it to modify the data. So we don't assign it to oil reserves like we did here with the equal sign. Instead, we just write it down like this. And we have the result displayed here now. We could think of a new name for a new variable, factor table or something like that, assign this comment to it and run it. And then, instead of the table appearing here, we will have a new object here. And this object contains exactly the same table we've seen displayed before. So if you just want something displayed, if you don't want it saved up here, then you don't need to use the equal sign. The second point is that there are multiple ways to access columns within an R table. So far, we primarily used the pipe to signal that we are referring to a data set, and then we only wrote the name of the column here. And this is typical tidyverse style. But here I use the other option, which is to give the name of the data set, use the $sign, and then list the name of the column I would like to look at. If you have a data set like this and type in the $sign, R will also have this autocomplete, which shows you what columns the data set has. It is very convenient to avoid writing mistakes. So R code can have different structures depending on what you are trying to accomplish. The next aspect we will look at is filtering values and working with strings. You may have already noticed, if I run this variable, most of the entities I called countries are indeed countries, Algeria, Angola, and so on. But not all of them are. There are some rows which describe the oil reserves of some entity that is not a country. Here, the Canadian oil sands. Obviously, these are part of the Canadian oil reserves, but they have a separate row in the dataset. This can be problematic because if we want to do statistical research, we cannot count the same oil reserves twice. So we will want to remove the Canadian oil sands because the reserves they contain are already contained in the Canadian reserves. And to do that, we need to filter the dataset and we need to work with strings. We have looked before at the select command, which allows to pick a column. The filter command is the counterpart, which allows to pick a row. And it is structured differently from the select command because in R, rows don't have names. They have this index here, but they don't have names. Columns have names because columns represent variables. But for rows, you don't usually say, I would like to select row 5 or something like that. Instead, you filter rows according to certain criteria. In our case, we want to remove all rows that refer to the Canadian oil sands. But if we look closely at the data, we will see that there are also some other values in the country column that we will want to remove. Canadian oil sands are most obviously because they are on the first page of this table, but this table has 72 rows. And it is a repeating occurrence that, for example, the European Union is its own category, even though its member states like Denmark are also listed. So this is another case where we want to remove the European Union because we only want to look at country data. More severe, there is this whole category which summarizes the oil reserves of certain regions. Total Africa, total Europe, total North America, even total world. We want to remove these aggregate categories as well. Now we could filter them out one by one. We could filter, give me all rows except total Africa. Filter, give me all rows except total Asia Pacific, and so on. But that would obviously be quite a lot of work. And we want all of these rows removed. So we do it all at once, working with strings. For this, there is what is called stringer. Stringer is part of the tidyverse, and its comments typically start with this prefix str. What this comment will do is it will filter the data set for any country variable that contains the letters total. Now, again, I use this exclamation mark, which means not in R. So the data set I will be given out will contain all rows except for the ones which were detected by stringer to contain the letters total in the country column. We will also see that this changes the size of the data set again. So if you look up here, you can see that it has lost nearly 400 observations because of this. Now, working with strings can also easily become more complex. We do not have the time to do this here, but if you want to conduct some sort of textual analysis for a term paper or something like that, I think it is definitively worth looking into. Now, we can again check that we have removed all the values we do not want anymore in the data set. As we can see, the number of rows using the Canadian oil sands has dropped from 41 to 0. So we have been successful in removing these observations. We can also check that we have removed the European Union and the other values. As I mentioned, the statistical review of world energy data is an Excel file with several sheets. And so far, we have only looked add one of these sheets, the one containing the oil reserves. Now we will add the information from a second Excel sheet to a table so we can do a regression with it. And by and large, this is the same code I already showed to you, but you will have to slightly modify it for every table. For example, the number of columns in the new table, which is about renewable power, is different. So I had to change the values in the select statement. This is something you will have to look up once you loaded the table into R. And because it is renewable power, of course, I choose other variable names. Again, there is country data. This time the unit of measurement are terawatt hours, and it is how much renewable energy a country produces within a specific year. We will want to combine the two into a single table, and for this we will use a join. Now, joins at first may seem fairly straightforward. We have the renewable energy table, which is in a very similar format in which the oil reserves are. And we can simply add the renewable energy terawatt hours value here and have all the correct numbers appearing here by telling the program that it should match these two tables by country and year. But there are a few things we will have to consider. First, the oil reserves data starts in 1980. So what is supposed to happen with terawatt hours data from years like 1965? There are two possibilities. One possibility is to add these, and then the oil reserves for this year would be not available because they are not in the data. The other possibility is to omit them. Depending on which of the two you choose, you use either a full join or an inner join. The inner join does not create any new not available data, but it also means that it does not include data which is only available in one of the two tables. So for example, these values here in an inner join will disappear because there are no corresponding oil reserve values for them. The full join will keep them, but as I mentioned, it will create the not available values. And I will briefly show the two to you. This is the full join. You mention which two tables you want to join, and you mention by which columns you want to join them. The inner join has exactly the same structure, except we specify that we want an inner join instead of the full join. And of course, we should also give the two different names, because else one will override the other. As we can see, the full join dataset is considerably larger than the energy dataset, because the energy dataset starts in 1980 and the full join dataset does not show not available values at the top, so you can't see it here right away, but we can sort by year, and we see that it contains these observations from 1965, for which we have no oil data. So full joins tend to give larger results. There's also the option to perform a right join or a left join. A right join keeps our observations from the right table, but only the matching ones from the left table. For the left join, it is in reverse. Quite intuitive, I think. Now, to finish the workshop, we will conduct a quick regression. We will try to see if the oil reserves have an impact on the renewable energy production in a country. It's possible that countries which have large oil reserves decide, oh, we have our own oil reserves. We have very cheap oil available, therefore we don't need to invest in other forms of energies. We don't need to invest in renewable energies. Now, for regressions, I like to use the fixes package. It does not make a lot of difference for a workshop like this because the dataset is very small, but the fixes package is fairly fast for larger datasets. And regressions in R are always created like this. Here you specify the type of regression, so in our case, ordinary least squares, and any fixed effects. Fixed regression starts with this FE prefix. Then within the regression, you specify what is the explanatory variable and what will be explained. So in our case, we want to find out if oil reserves have an impact on renewable energy produced. These are the oil reserves. This is the renewable energy production. And we will also control for the year. So this part here denotes that what comes after is a fixed effect. We will use year fixed effects to control for the fact that as years went by, on one hand, more and more oil reserves were discovered because of better technology, and on the other hand, renewable technology has improved as well. We don't want that to distort our results. We just want to compare things that happened in the same year, so we use year fixed effects. Now, it is common practice to also save the regression result in this environment pane, and then we can look at the regression result with the summary function. This part here defines that I will use cluster standard errors. There are a lot of ways in which you could define standard errors. So this is something you will want to think about if you insist on running a regression on your own. But this here is just a demonstration that you can easily run regressions with tidy data. And there we have it. Oil reserves have a negative influence on the renewable energy produced. It is not a very large effect, but it is statistically significant. The last point I would like to address are the sources of my workshop. So I hope this workshop gave you a good introduction into the tidyverse. Its main developer is Hadley Wickham, and he wrote a book called R for Data Science on how you can use R if you want to use R and the tidyverse to work with data in all kinds of manners. The book is freely available online on his website. He has some co-authors. He has some co-authors in the tidyverse as well, but he's really the main developer. And of course, it's much more detailed than a tutorial with 1.5 hours. So if you are interested in continuing with the topic, I highly recommend you take a look at it. In case you are more interested in the regressions and the types of things you can do with the fixes package, which I was only able to introduce briefly here, It was created by Lauren Birch. His website contains more information on it if you want to begin with some regressions, how you can do this. So you can take a look at that if it is what you're interested in.